Most neutrons created in a core are prompt neutrons, approximately 99% of them. The rest are called delayed neutrons and come into existence only after a fission product beta decays, as seen in the figure here. First, the fission product must exist, and then after some time t, which is greater than the mean neutron generation time, for prompt neutrons, the fission product will emit a beta particle. This can be either a beta plus or a beta minus. Then, the fission product will decay again, releasing a neutron. Call beta a unitless quantity, the fraction of neutrons that are delayed, that is, not prompt. Typically, beta is chopped up into I distinct groups that each represent a different neutron generation time. Suppose that little I indexes big I, then the total delayed neutron fraction will equal the sum of the delayed neutron fractions for each group. By convention, beta 1 has the longest generation time, and beta I has the shortest. Choosing 6 delayed neutron groups is fairly standard. You can see the breakdown of these groups in this table. Taking into consideration delayed neutrons, the source of prompt neutrons in the diffusion equation is now represented by 1 minus the delayed neutron fraction times nu sigma f times the flux. Call C sub I of t the concentration in units of 1 over centimeters cubed of the ith delayed neutron group. If we also call T1/2 I the half-life of the ith group, we can define a lambda I as the decay constant of the ith delayed neutron group, such that lambda I equals the natural log of 2 divided by the half-life of the ith group. The delayed neutron source term is then the sum for I and I of lambda I times Ci of t. Note that there are beta I nu sigma f phi neutrons created from the ith group in each neutron generation. Therefore, the changes in the concentration Ci of t is governed by a sources minus losses expression similar to the setup for the diffusion equation. Namely, the time derivative of the ith group's concentration is equal to the ith group's fraction times nu sigma f times the flux minus the decay constant for the ith group times its concentration. Therefore, we can recast the diffusion equation as 1 over the speed times the time derivative of the flux equals 1 minus the delayed neutron fraction times nu sigma f times the flux plus the sum of for all I and I of the decay constant of the ith group times the concentration of the ith group minus our normal neutron losses due to absorption and leakage. Therefore, we have obtained a system of I+1 equations and I+1 unknowns, namely phi of t and the concentrations Ci of t. This system should be solvable. From here we can derive the point kinetic equations. To do so, let's first group the flux terms together. While the left-hand side stays the same, the right-hand side now becomes 1 minus the delayed neutron fraction times nu sigma f minus sigma a minus our leakage term dB squared, all multiplied by the flux, plus the sum of the decay constants for the ith delayed neutron group times their concentrations. Secondly, let's substitute the flux as a function of time for the speed of the neutron times the number density of the neutrons. Doing so makes it so that the time derivative of the neutron number density is equal to 1 minus the delayed neutron fraction times nu sigma f minus sigma a minus our leakage terms, multiplied by the speed of the neutrons times the neutron number density, multiplied by the ratio 1, which is here represented by nu sigma f divided by nu sigma f, plus the source of delayed neutrons, lambda I Ci of t. Multiplying the nu sigma f in the denominator in the first term on the right-hand side, we see the following expression. Note that here, 1 minus sigma a plus dB squared divided by nu sigma f is just the reactivity rho. Additionally, V times nu sigma f is just 1 over the mean neutron generation time, L star. Furthermore, we can substitute phi equals V times the neutron number density back into our concentration equations. Thus, the point kinetic equations are given as the time derivative of the neutron number density is equal to rho minus the delayed neutron fraction divided by the mean neutron generation time times the neutron number density plus the delayed neutron sources lambda I times Ci of t. The time derivative of the concentration of delayed neutrons dCi of t dt is equal to the delayed neutron fraction for the ith group divided by the mean neutron generation time times the neutron number density minus lambda I Ci of t. In general, these equations can be extended to be a function of energy, position, material, and direction. However, we won't be doing any of that here. As a brief aside, it is important to note that the reactivity is often scaled by the delayed neutron fraction. Doing so measures the reactivity in units of dollars, such that $1 equals the reactivity divided by the delayed neutron fraction. Of course, 1/100th of a dollar is 1 cent.